This is a joint work with my colleague Ke and my advisors Tao and Sebastian. So this is the basic setting of private information retrieval. There's a server who holds a database with n items, and there's a client who wants to get an item from the database without revealing which item to the server. Why we're interested in such protocol? Because PIR is a very useful building block for many applications. For example, in anonymous communication, my friends and I can fetch messages from a server using PIR to hide our communication linkage. You can also use PIR for private search, which allows you to search for your interested document containing a target keyword while hiding the keyword from the server. In all these applications, what we care about is the cost of PIR, in particular, communication and computation costs. And when we talk about cost, we will usually speak in terms of the database size n, because in real-world applications, the databases are large, and n is usually the dominant factor of the cost. So how do we construct PIR? A trivial solution is just to have the client download the entire database, no matter which item it wants to retrieve. This works, it's private, but it has very high cost. The communication is linear in the database size, so this has no hope to be used in practice. Fortunately, there are many works that construct PIR with communication cost that is sublinear in the database size, and some even have optimal cost. But on the other hand, achieving sublinear computation is not that easy. Intuitively, when the server answers a query, even if a single item is omitted, this will click the information that this item is of no interest to the client. So actually, there's a lower bound says that the linear computation for the server is necessary unless we do some sort of preprocessing. Many works explore the power of preprocessing, and they construct PIR solutions with sublinear computation cost. And in this work, we focus on a recently proposed model called offline-online PIR. In this model, the client and the server first interact in an offline phase, where the server does linear work to preprocess the database and generate a small hint, which is sent to the client. Then in the subsequent online phase, the client can issue many queries to the server, and the server can answer each of them using only sublinear work. The hint and the database match in a way that the client can reconstruct the item it wants using the hint and the server's answers. So in short, these offline-online PIR schemes give us sublinear communication as in prior works, and the linear computation in the offline phase can be amortized over many online queries. So this also gives us sublinear computation. Okay, so these are very good constructions, but let's see what happens if we apply this offline-online model to real-world applications when database can change. So let's consider a private media service where a content server holds a bunch of news articles, and the client wants to use PIR to retrieve its interested articles. At the beginning, a new client comes, and the server does a linear preprocessing and generates a small hint sent to the client. A few minutes later, when the client wants to fetch its interested content, it issues a few PIR queries to the server, and the server can process them very fast using sublinear work. But shortly after, there are two more new articles added to the database. So now, can the client issue queries? Remember that the hint and the database should match in a way that the client can reconstruct the item it wants. But in this case, the hint and the updated database no longer match. So now we can see an issue here. The solutions in the preprocessing model actually works only for the static database. But in practice, database can change. So given this, how do we still can apply this offline-online PIR to applications when database can change? A first straightforward solution is just to have the server redo the preprocessing for the updated database. So now the client will discard the old hint and obtain the new hint from the server and use the new hint to do the queries. This works, but it requires the server to do the amount of the work linear in the database size for each time of the change, even if the change is very small compared to the database size. Can we do better? Another solution would be have the server to build a new database that contains only the added items. Now the client and the server does an offline phase where the server preprocesses this new small database and generates a hint. So in this case, the server only does the work linear to the number of additions, which is great. But there are issues arise when the client wants to make queries to hide which part contains the item the client wants. It has to issue PIR query to each of the database, so this increases the client communication and computation. And furthermore, if there are more items added to the server database, it's very hard for the server to manage multiple databases, and the client has to issue many queries, even if it wants to fetch a single item. So our solution to handle the database changes preserves all the low-cost property of the PIR solutions for the static case. In particular, in our case, the server just manages a single database, and when our changes come, the server will do a minimum but necessary work, which is linear in the number of additions, and generates a small hint. Then the client will use the hint to merge with the old one and generates an updated hint that matches the updated database. And after that, the client can use this new hint to make queries as in the offline-online PIR, where we get sublinear computation for the server and sublinear communication. Our solution is based on two recently proposed constructions in the offline-online model. And in this talk, I'll only focus on the first one by Corrigan, Gibbs, and Kogan. And after I talk about our solution, I'll briefly touch on the experimental results. So in their work, the offline phase is executed as follows. The client first samples square root and random sets, where each set contains square root and random indices from the database range from 1 to n. The client sends the sets to the server, and the server responds with the XOR of the items indexed by the sets. So as a result, the client will store a hint consisting of the sets and the corresponding parity h. But as you can see, if the client sends the sets in a clear, it requires a communication larger than n, which we'll want to avoid. So they propose a technique to compressively represent the set using the short key. So now the communication is reduced to sublinear, and the hint is also small. I will skip their online phase, but to ensure their scheme is correct and private, we have to impose two requirements on the hint. So the first one is that each set should be random over all the indices of the database. So in this case, from 1 to n. And the parity h should match the set specified by the key k. So now, as you can see, if there are n more items added to the database, the old key k1 is no longer a valid hint, because this key k1 specifies a set that contains only indices randomly sampled from the range from 1 to n. So the first challenge is how can we update each set to be random over the new range? And after we get the new keys, how can the client obtain the parity that match the key? The first question can be easily answered by just resample fresh keys so that each key represents a set that is random over the new range from 1 to n plus m. But in this case, the server has to compute the XOR for the new sets, which is basically essentially preprocessing from scratch. So our goal is to answer those two questions with low server computation cost and low communication. Our first contribution is a randomized algorithm to update the keys. And a key property of the algorithm is that it keeps most of the indices in the existing sets, so the set will not change much. And even if the set changes, we still can keep some short representation of the set, so the hint stored at the client is still kept succinct. These two properties translate to a hint update procedure, which has low computation and communication cost. To specify, the client will first send the difference between the old sets and new sets to the server, and the server responds with the XOR of the item based on the set difference. Then the client can use the server's answers to update the hint that matches the updated database. And remember that we have minimum modification of the sets, so this results in low server computation. And we have compressed representation of the set difference, so this results in low communication cost. And the question we're asking in the evaluation is that, how does this construction save the server cost? So we first let the server do the preprocessing for the entire database, and then we add 1% data to the database, and then we do the hint update procedure and measure the server computation time. As you can see, there are 50 more improvements of our approach compared to the strawman. Okay, so the takeaways of the talk are, first, we identify a problem of the PIR solutions in the preprocessing model, and these solutions doesn't work well when the database can change. And then we propose techniques to make the hint mutable for this offline-online model. In particular, our solution has server cost only proportional to the number of changes, but not the entire database size. And this solution works well for applications when changes are frequent but small. We'll have more evaluation results for the Tor application in our paper, and our code is available. Thank you.